All right, so today we're diving deep into the world of nanocatalyst synthesis,
Oh, yeah.
pulling some incredible insights from Professor Pedro Camargo's Nanocatalysis lecture at the University of Helsinki.
Mm-hmm.
This is going to be super relevant to anyone working with nanomaterials in the lab,
For sure.
especially if you're,
Yeah.
trying to control the size, shape, and composition of those nanoparticles for optimal catalytic activity.
Absolutely.
So let's jump right in.
Okay.
One of the things that really stood out to me was just how many different methods there are for nanocatalyst synthesis.
Oh, yeah. There's a lot of different approaches out there.
It's not like a one-size-fits-all kind of situation.
Definitely not.
So how do we even begin to choose the right method for our specific needs?
Well, a good starting point is colloidal synthesis.
Okay, colloidal synthesis.
Yeah, it's widely used, especially in research settings.
Right.
And it gives you a remarkable degree of control over nanoparticle formation.
But I remember from my own lab experience that colloidal synthesis can be a bit tricky,
Oh, yeah.
especially when it comes to preventing those nanoparticles from clumping together.
Absolutely. You're talking about aggregation.
Right. Aggregation.
Yeah, and that's where the concept of surface energy comes into play.
Okay, so surface energy, what is that exactly?
So think about it this way.
Yeah.
Nanoparticles, they have a high surface area to volume ratio, right? And that means that the atoms on the surface,
Yeah.
they have fewer neighbors.
Yeah.
And that leads to kind of like an energetic instability.
They're not happy being on the surface.
Exactly. They want to minimize that energy.
So they try to clump together to reduce that exposed surface area.
Precisely. They want to find more neighbors and lower their energy state.
So high surface energy equals unhappy nanoparticles.
You got it.
And unhappy nanoparticles equals aggregation.
And aggregation equals, it equals a loss of control over those nanoparticles.
Right, because if they're all clumped together,
Yeah,
we can't really control their size or shape anymore. And that's bad news for us in the lab.
definitely.
So how do we even quantify this surface energy?
Well, Professor Camargo actually provides an equation.
Oh, an equation.
It's sigma equals 1/2 NB times the sum of epsilon rac.
Okay, I'm not sure I'm going to memorize that one.
Yeah, no need to memorize it.
But it's good to know that there's a way to actually measure it.
Absolutely.
And what are those symbols all about?
So sigma, that's the surface energy.
Okay.
NB, that represents the number of bonds you have to break to create a new surface.
Oh, yeah.
Epsilon, that's the strength of those bonds.
Mm-hmm.
And wheel rac, that's the area occupied by each atom on the surface.
So essentially it's telling us that surface energy is a function of how many bonds we have to break,
Yeah,
how strong those bonds are,
right.
and how densely packed those atoms are on the surface.
Exactly.
So if we want to stabilize those nanoparticles and prevent them from aggregating,
Mm-hmm.
we need to find ways to manipulate those factors.
Precisely.
And that's where those clever synthesis techniques come in. Professor Camargo talks about solution phase synthesis,
Yeah.
which he breaks down into two main strategies:
Mm-hmm.
thermodynamic equilibrium and kinetic approaches.
Those are the two main categories.
Okay, so can we break those down a bit further?
Yeah.
What's the difference between a thermodynamic approach?
Okay, so with a thermodynamic approach,
Yeah.
it's all about controlling the energy landscape.
The energy landscape.
Yeah, you're basically trying to guide those nanoparticles towards the desired size and shape by manipulating the driving forces behind nucleation and growth.
Okay, so we're kind of like setting the stage for them to grow in a certain way
Exactly.
by controlling the energy of the system.
Right.
And what about the kinetic approach?
The kinetic approach,
Yeah.
it's more about controlling the rate of growth.
Okay, so like speed control.
Yeah, like a speed limit for nanoparticle growth.
Interesting.
You're often limiting the supply of precursors to slow things down.
So we're either gently coaxing those nanoparticles into the shape we want, or we're carefully controlling their growth spurt.
Precisely, and both approaches can be really effective.
Right, it just depends on what we're trying to achieve.
Exactly.
And one thing that Professor Camargo really emphasized
Yeah.
was the importance of achieving monodispersed nanoparticles.
Monodispersity, that's the holy grail.
Yeah. So for those of us who maybe haven't heard that term before,
Mm-hmm.
what exactly does monodisperse mean?
It means that those nanoparticles,
Yeah.
they're essentially identical
Identical in what way?
in terms of size, shape, composition,
wow.
even crystalline structure.
So like a perfect batch of nanoparticles.
Yeah, as close to perfect as we can get.
And why is that so important?
Well, think about it.
Yeah.
If you're running a catalytic reaction
Mm-hmm.
and your nanoparticles are all over the map in terms of size and shape, some might be super active, others might be sluggish.
And you don't really know which is which.
Exactly.
So your results become kind of unpredictable.
Totally. It's hard to draw any meaningful conclusions if you don't have that consistency.
But if you have monodisperses nanoparticles,
Yeah.
you have a much better understanding of that structure-activity relationship.
Absolutely.
And your results are much more reliable.
Right. Consistency is key.
So how do we actually achieve this monodispersity?
Well, it all comes down to controlling the nucleation and growth processes.
Okay, so let's talk about those.
Yeah,
Professor Camargo dives into the nitty-gritty of these mechanisms,
he does.
which seems pretty crucial for anyone trying to make these monodispersed nanoparticles in the lab.
Absolutely.
So let's start with nucleation.
Okay, so nucleation,
Yeah.
that's the very first step in nanoparticle formation.
Right. It's like those initial seeds.
Yeah, those tiny clusters of atoms that come together.
And we want those seeds to be as uniform as possible.
Exactly.
So how do we control that?
Well, Professor Camargo talks about this concept of burst nucleation.
Burst nucleation.
Yeah, it's like a sudden burst of nanoparticle formation, where all those initial nuclei form very quickly.
So it's like a synchronized starting line for those nanoparticles,
Exactly.
and then they all start growing from there.
Right.
And that helps to ensure that they all end up roughly the same size.
Yeah, because they all have similar growth histories.
I like that, a synchronized starting line.
It's a helpful analogy.
So we've got those seeds formed,
Mm-hmm.
and they're all starting to grow.
Right.
But now we need to make sure that they all grow at a similar pace.
Exactly.
So let's talk about growth mechanisms.
Okay, so Professor Camargo actually breaks down nanoparticle growth into 4 major steps.
4 major steps, okay.
Yeah, and assuming that the diffusion of those growth species is fast.
Growth species, those are like the building blocks of the nanoparticles.
Yeah, those atoms or molecules that add on to those initial nuclei.
Okay.
So assuming fast diffusion, there are 2 main pathways for growth:
Okay, 2 pathways.
layer by layer growth and polynuclear growth.
Can you paint a picture of what those look like?
Yeah, so imagine you're building a brick wall.
Okay, I'm imagining a brick wall.
In layer by layer growth,
Mm-hmm.
you're carefully laying down one brick, then another.
Okay, so nice and slow.
Exactly. It's a slow, meticulous process.
And what about polynuclear growth?
Polynuclear growth is more like throwing a bunch of bricks at the wall and letting them stick wherever they land.
Oh, okay, so less control.
Much less controlled, it's faster, but you end up with a more irregular structure.
So for making monodispersed nanoparticles,
Mm-hmm.
we're aiming for that layer by layer growth.
Right, that slow and steady approach.
Because that gives us more control over the final size and shape.
Exactly.
We want to encourage what's called diffusion-limited growth,
Diffusion-limited growth.
where those growth species arrive at the nanoparticle surface in a controlled manner.
Right.
So no brick throwing allowed.
Exactly. Precision is key.
So how do we actually favor this diffusion-limited growth in the lab?
Well, Professor Camargo gives us some practical tips.
Okay, let's hear them.
One way is to keep the concentration of those growth species low. Okay, so not too many bricks flying around.
Right.
What else?
We can increase the viscosity of the solvent.
Make it thicker.
Yeah, that slows down the movement of those growth species.
Okay.
We can even introduce diffusion barriers at the particle surface.
Diffusion barriers like obstacles.
Exactly, like little fences that make it harder for those growth species to reach the surface.
So it's all about fine-tuning those reaction parameters.
Yeah.
To achieve that delicate balance between promoting growth,
Right?
but preventing those nanoparticles from going rogue
Absolutely, yeah.
and forming those big clumps we were talking about earlier.
Aggregation is the enemy.
So we're not just controlling the size,
Mhm.
we're also controlling the shape.
Precisely. And that brings us to the next level of nanoparticle design.
Shape control.
Shape control.
Yeah. That's where things get really exciting.
Oh, yeah.
Because as we know, different shapes can have totally different catalytic activities.
Absolutely.
It's not just a matter of aesthetics.
It's about functionality.
Yeah.
And Professor Camargo uses metal nanoparticles
Mm-hmm.
with a face-centered cubic structure
FC.
to illustrate this point.
Yeah, the FCC structure.
Most of us are probably familiar with that.
Right, it's one of the basic crystal structures.
But it's worth revisiting in this context.
Definitely.
So let's imagine a cube.
Okay, a cube.
Each face of that cube,
Yeah,
those facets,
the facets.
they expose a different arrangement of atoms.
Right, different crystallographic planes.
And those different arrangements,
Mm-hmm.
they interact differently with the molecules involved in a chemical reaction.
Exactly. They have different affinities for certain molecules.
So by controlling the shape of the nanoparticle,
Yeah.
we're essentially engineering which facets are exposed
Exactly.
and how they interact with those reactants.
We can favor the formation of certain facets
Yeah.
that are particularly good at grabbing and activating certain molecules.
So it's like we're sculpting those nanoparticles,
Yeah,
selectively exposing those catalytic hotspots.
that's a great way to put it.
And to demonstrate this in action, Professor Camargo dives into a specific example.
Right.
The synthesis of silver nanoparticles.
Silver nanoparticles, yeah.
Using the polyol method.
The polyol method, it's a classic.
So what's so special about silver nanoparticles?
Well, they're really versatile.
Versatile. How so?
We can make nanowires, nanocubes,
Oh, wow.
all sorts of fascinating structures.
So they're like the chameleons of the nano world.
Exactly.
They can take on all these different forms.
Right, and those different forms,
Yeah.
they have different catalytic properties.
Okay, so what makes the polyol method so special?
The polyol method, it allows for exceptional control over the final morphology.
Morphology, that's just a fancy word for shape, right?
Yeah, it refers to the shape and structure of the nanoparticles.
Okay.
And it relies on this interesting solvent,
What solvent?
ethylene glycol.
Ethylene glycol.
Yeah, and it acts as both a solvent and a reducing agent.
A 2-for-1 deal.
Exactly. It simplifies the process.
Okay, and is there anything else involved?
Yeah, there's also a polymer called polyvinyl pyrrolidone,
Polyvinyl pyrrolidone.
or PVP for short.
PVP. That rings a bell.
Yeah, it's a common capping agent.
Okay.
And it's crucial for controlling the shape of those silver nanoparticles.
So PVP is like a molecular sculptor.
Molecular sculptor, I like that.
It's guiding the growth of those nanoparticles.
Precisely. It binds preferentially to specific facets of the growing silver nanoparticles.
So it's kind of like directing the traffic of those silver atoms.
Exactly. And by adjusting the concentration of PVP and other reaction parameters.
You can steer those nanoparticles towards specific shapes.
Right, like those nanowires or those beautifully defined nanocubes.
And Professor Camargo actually uses some really cool visuals.
Oh, yeah, he does.
To illustrate how this works.
Yeah, those visuals are super helpful.
Step-by-step images showing how those silver nanoparticles evolve from tiny nuclei to well-defined nanocrystals.
It's amazing to see it.
Okay, but before we get too carried away with the magic of the polyol method,
Yeah.
Professor Camargo reminds us that there are other techniques out there.
Oh, yeah, there are a bunch of other methods.
So let's explore some of those next.
Absolutely. We've just scratched the surface of nanomaterial synthesis.
Okay, so we've delved into colloidal synthesis,
Right.
explored how to control those nanoparticles in solution. But what about other techniques?
Yeah. There's a whole world of other methods out there.
Like what?
Well, let's step away from the solutions for a bit
Okay.
and venture into the realm of vapor phase synthesis.
Vapor phase synthesis.
Yeah.
So we're talking about reactions in the gas phase?
Exactly.
That sounds pretty intense.
It can be, but it's also incredibly powerful.
Powerful in what way?
Well, for one, it's highly scalable.
Scalable.
Yeah, think about industrial production, like
sure.
the production of carbon black.
Carbon black.
Yeah.
You know.
Stuff in tires.
Exactly. It's used in tires, pigments.
Oh, wow.
All sorts of applications.
Yeah.
And that's made using vapor phase synthesis.
On a massive scale.
But we're talking about generating those tiny particles.
Yeah, those carbon black nanoparticles.
Directly from gaseous precursors.
Precisely.
And it's not just carbon black, right?
No, not at all.
We can use vapor phase synthesis to make other materials as well.
Yeah, a whole variety of materials.
Like what?
Metal oxides, nitrides, carbides.
Well, all from those gaseous building blocks.
Exactly. And the beauty of it is the control we have over the reaction conditions.
Okay, so what kind of control are we talking about?
Well, we can manipulate the temperature, the pressure,
Okay.
the gas flow rates.
And by tweaking those parameters, we can fine-tune the properties of those nanoparticles.
Precisely.
That sounds pretty powerful.
It is, but of course there are some challenges.
Challenges.
Yeah, especially when we're aiming for that prized monodispersity.
Right, because those nanoparticles love to clump together.
Exactly. Agglomeration can be a real headache.
So how do we prevent that?
Well, one of the main challenges with vapor phase synthesis is the lack of those stabilizing agents.
So stabilizing agents.
Yeah, those PVP molecules we talked about earlier.
Right, those molecular sculptors.
Exactly.
That help to prevent aggregation in colloidal synthesis.
Right, but in the gas phase,
Yeah.
we don't have that luxury.
So those nanoparticles are more prone to colliding and sticking together.
Especially in that hot, chaotic, gaseous environment.
So it's like a mosh pit of nanoparticles.
A mosh pit of nanoparticles. I like that.
All bumping into each other.
And forming those larger aggregates.
Definitely not ideal.
Nope, not if we want those well-defined monodispersed particles.
So how do we tame that nanoparticle mosh pit?
Well, one approach is to carefully control those reaction conditions.
Okay, so like a choreographer for nanoparticles.
Exactly. We can adjust the temperature, the pressure,
Okay.
the gas flow rate.
To minimize those chaotic collisions.
Right. It's all about precision and finesse.
Even in that intense gaseous environment.
Precisely.
What other strategies are there?
We can also introduce a quenching gas.
Quenching gas?
Yeah, it's like a cooler stream that rapidly cools down the reaction mixture.
So it's like hitting the pause button on that nanoparticle mosh pit.
Exactly, before those particles have a chance to glom onto each other.
I like that, hitting the pause button.
It's a helpful way to think about it.
So we've got vapor phase synthesis, scalable, but with those agglomeration challenges.
Right.
What other techniques should we be exploring?
Let's switch gears and dive into the world of surface chemistry.
Surface chemistry?
Yeah, specifically ion adsorption synthesis.
Ion adsorption synthesis. Okay, break that down for me.
So this method takes advantage of the electrostatic interaction.
Electrostatic interaction.
Yeah, between ions and charged sites on a support material.
So we're talking about attracting ions to a surface.
Exactly, like molecular magnets.
Okay, so what's the big picture here?
So imagine you have your support material,
Okay.
often a metal oxide, with a surface covered in these tiny charged sites.
Charged sites.
Yeah, like little hooks.
Okay.
And then you introduce a solution containing metal ions.
Metal ions. Those are the ingredients for our nanoparticles.
Right. And if the charges are right, those ions will latch onto those hooks.
So they're decorating the surface.
Exactly. They're anchored to those specific sites.
And what's the advantage of doing that?
Well, for one, it allows us to create highly dispersed nanoparticles.
Highly dispersed.
Yeah, because those ions are tethered to those sites. They're less likely to wander off and form those dreaded aggregates.
Right. It's like we're giving each nanoparticle its own designated parking spot.
A designated parking spot. I love that.
No more mosh pits.
Exactly. Much more organized.
So how do we control which ions get those parking spots?
Well, we can manipulate the pH of the solution.
The pH?
Yeah, that changes the charge on the support surface. And that allows us to select which ions get attached.
So it's not just about attracting any ion.
No.
We can be selective.
Precisely. And this level of control is incredibly powerful.
So we can tailor the composition and distribution of those nanoparticles on the support.
Exactly. And that can have a huge impact on their catalytic performance.
This is starting to sound like a very versatile technique.
It is, and it's particularly well suited for those supported catalysts.
Supported catalysts.
Yeah, where we want those active nanoparticles dispersed on a high surface area support material.
Right, those scaffolds we talked about earlier.
Exactly. They provide a platform for those nanoparticles to do their catalytic magic.
And speaking of supported catalysts, there's another method that's commonly used for creating them.
Oh, yeah.
Deposition precipitation.
Deposition precipitation, right?
Wait, what's that all about?
So it's all about manipulating the solubility.
Solubility.
Yeah, of those metal precursors.
Okay.
To coax them into depositing onto that support surface.
So we're kind of pushing those precursors out of the solution.
Exactly. We're making them less soluble.
And they end up on the support.
Right. And the support itself plays a key role here.
Okay. How so?
It often provides those favorable nucleation sites.
Nucleation sites.
Yeah, those spots where those metal precursors can start to crystallize.
So it's like a landing strip for those precursors.
A landing strip, that's a good analogy.
So we're forcing those precursors to crystallize, but we're directing that crystallization to happen specifically on the support surface.
Precisely. And this offers some really nice advantages.
Like what?
Well, we can control the loading of those precursors,
No.
the size and dispersion of those resulting nanoparticles, even the interaction between those nanoparticles and the support.
So it's a very powerful technique for building those supported catalysts.
It is a real workhorse in both research and industry.
Okay, so we've covered colloidal synthesis,
Right.
vapor phase synthesis, ion adsorption,
Yeah.
and deposition precipitation.
That's quite a range of techniques.
It is. Are there any other tricks up our sleeve?
Absolutely. Let's explore co-precipitation.
Co-precipitation.
Yeah, it's a bit different.
Different how?
Well, instead of synthesizing the support and the catalyst separately, we do it all at once.
All at once, so it's like a 2-for-1 deal.
Exactly. It streamlines the process.
Okay, I'm intrigued. How does that work?
So we start with a solution containing precursors for both the support and the catalyst.
So it's like a molecular soup.
A molecular soup. I like that.
With all the ingredients mixed together.
Right. And then we adjust the conditions to trigger the formation of a solid precipitate.
A precipitate.
Yeah, a solid that forms from that solution.
And that precipitate contains both the support and the catalyst.
Precisely. They're intimately intertwined.
So it's like we're creating this intricate mixture
Yeah.
where those catalytic components are woven into the support material.
From the very beginning.
And that can enhance its performance.
Often, it leads to a more homogeneous distribution of the catalyst.
That sounds pretty elegant.
It is, but there are often some additional steps involved.
Additional steps.
Yeah, like calcination.
Calcination.
Remember, heating the material in air.
Right, to activate the catalyst.
Exactly. So coprecipitation sets the stage, and calcination transforms it into that final active form.
So it's a very versatile technique.
It is, especially when you're looking for that homogeneous distribution.
Okay, so we've covered a lot of ground here.
We have.
From colloidal crafting to vapor phase mosh pits.
Molecular soup and landing strips.
It's amazing how many ways there are to create these nanomaterials.
It is. Each method has its own strengths and weaknesses.
Right, making it suitable for different applications.
Exactly.
Okay, before we wrap up this whirlwind tour, is there one more technique we should add to our arsenal?
Let's not forget about impregnation and drawing.
Impregnation and drawing?
Yeah, a classic technique.
Okay, so what's involved in that?
So picture a sponge. That's our porous support material.
Okay.
And we're going to dip that sponge into a solution containing the catalyst precursor.
The catalyst precursor.
Yeah, the ingredient for our active catalyst.
So the support is soaking up that precursor like a thirsty sponge.
Exactly. It's all about ensuring good contact between the precursor and the support surface.
Well, it sounds simple enough.
It is relatively straightforward.
But are there any variations?
Oh, yeah. There are two main types of impregnation.
Okay, let's hear them.
Incipient wetness impregnation.
Incipient wetness impregnation.
Yeah, that's like a gentle soak.
A gentle soak.
We add just enough solution to fill those pores.
Okay.
No excess liquid.
So it's very precise.
Precisely. Minimizes waste and ensures even distribution.
And the other type?
Wet impregnation.
Wet impregnation.
That's more like a full-on dunk.
Full-on dunk.
We use an excess of solution.
Okay.
Submerging the entire support.
So it's a trade-off between precision and ease of use.
Exactly. The choice depends on the specific application.
Okay, so we've soaked our support.
Right.
Whether it's a gentle soak or a full dunk. What happens next?
Drying. Drying.
We need to remove that solvent.
Okay.
Usually water.
To leave behind that solid material.
Yeah, with that catalyst precursor dispersed throughout the support.
So we're squeezing out the excess liquid.
Like squeezing out that sponge.
And then what?
Often, drying is followed by calcination.
Calcination, that heat treatment.
Exactly, to activate the catalyst.
Okay, so impregnation and drying sets the stage for that final activation step.
Precisely.
It's a classic technique.
It is versatile and scalable.
Wow, this deep dive has really opened my eyes.
To the world of nanomaterial synthesis.
It's incredible how many different approaches there are.
It is, and as we continue to explore and refine these methods, who knows what incredible materials and applications await us.
So we've covered a whole lot of ground in this deep dive into nanocatalyst synthesis.
We have, from colloidal crafting to vapor phase mosh pits.
Ion parking lots, molecular soup, landing strips.
We really have explored a lot.
A whole arsenal of techniques for creating these tiny but mighty materials.
It's mind-blowing how many ways we can control these nanoparticles.
It really highlights the incredible ingenuity and creativity in this field.
So as we wrap up this deep dive, what are some key takeaways for our fellow grad students out there slaving away in the lab? What should they be thinking about as they're designing and synthesizing their own nanocatalysts?
Well, first and foremost, remember that size matters.
Size matters, yeah. I've definitely seen that firsthand.
It's all about that surface area to volume ratio.
Right, the smaller the particle, the more surface area it has relative to its volume.
And that means more active sites available for those catalytic reactions.
More bang for your buck, catalytically speaking.
Exactly. So it's not just about making nanoparticles, it's about optimizing their size for peak performance.
And we've explored a whole bunch of ways to do that.
We have, from adjusting reactant concentrations to using those clever capping agents like PVP.
Or even confining those nanoparticles in tiny reaction vessels.
Like those nano-sized reaction chambers.
It's amazing how much control we have these days.
And let's not forget about shape.
Shape, right. It's not just about aesthetics.
Not at all. The shape of a nanoparticle can have a dramatic impact on its catalytic activity and selectivity.
Because different facets, those exposed surfaces, can exhibit totally different catalytic properties.
It's like those nanoparticles have different personalities depending on their shape.
And we can manipulate those personalities by tweaking the synthesis conditions.
Precisely, we can favor the formation of certain facets over others.
So we're not just making nanoparticles, we're sculpting them.
Shaping them to expose those catalytic hot spots that we need for specific reactions.
And of course, composition is critical as well.
Absolutely. The choice of material can make all the difference.
Whether it's a metal oxide, a sulfide, or a combination of different elements.
We have so many options these days.
It's like having a molecular periodic table at our disposal.
And we can fine-tune that composition in so many ways.
Carefully selecting our precursors, adjusting the reaction temperature,
Even doping those nanoparticles with specific impurities.
to give them those extra superpowers.
Exactly. We can tailor those electronic and catalytic properties.
So we're not just chemists anymore, we're molecular architects.
Designing and building catalysts from the bottom up.
So as we look to the future of nanocatalyst synthesis, where do you see the field heading? What are some of the exciting frontiers out there?
Oh, there's so many possibilities.
Lay it on me.
One area that's particularly exciting is the development of even more sophisticated synthesis methods.
Even more sophisticated.
Methods that allow us to achieve atomic-level precision in nanoparticle design.
Oh, wow. Atomic level precision. That's next level.
Imagine arranging those atoms one by one to create the perfect catalyst.
That's incredible. It's like having ultimate control over matter.
And while it's still a challenging frontier, the possibilities are mind-boggling.
Catalysts with unprecedented activity, selectivity, and stability.
Catalysts that could revolutionize industries from energy to medicine.
Catalysts that can efficiently capture carbon dioxide, break down pollutants, even produce personalized medicines.
The potential is truly transformative.
And another exciting direction is the integration of these nanocatalysts into more complex devices and systems.
We're already seeing nanocatalysts popping up in fuel cells, sensors, even targeted drug delivery systems.
It's not just about making nanoparticles anymore. It's about putting those tiny powerhouses to work in the real world.
And as we continue to explore those unique properties of nanomaterials, I think we can expect to see even more game-changing breakthroughs.
This deep dive has been an incredible journey, and a huge thank you for guiding us through it.
It's been my pleasure, and I can't wait to see what the future holds for all of you budding nanomaterial scientists out there.
To all our listeners, keep exploring, keep experimenting, keep pushing the boundaries. And remember, the world of nanomaterials is vast and full of wonder. Go out there, make some amazing catalysts, and change the world.
Yeah.
Until next time, happy researching.